Hello everyone, I think we are ready to start. Let me introduce myself. My name is Sinkunan, Technical Engineer of Midas IT from Headquarter. So first of all, thank you for joining our webinar today. So today's webinar, the topic is high-speed to efficient design using dynamic analysis. So today's webinar, I will talk about the basic capabilities of dynamic analysis of high-speed train on bridge structure using Midas Civil. And I will show you how this can be done in Midas Civil and also how to check various results to see its effect on the structure. So this is the contents of today's webinar. So first I will talk about how and when the dynamic analysis is required for your project. And second is how to set up the eigenvalue analysis and how to set up the mass data for the structure for eigenvalue analysis. And then I will show you how to create time history load cases and then how to apply structural damping to to your model. And I will also show you how to generate train load using both dynamic analysis method, this function called train load generator, and also I will generate train load using static moving load analysis function in Midas Civil. And then I will apply these train loads generated from train load generator using dynamic nodal load function in Midas Civil. And then once we input all these factors and all this data, I will show you how to check those results and compare with dynamic analysis and static analysis. And I will finish off with a simple quick demonstration of all of this. So the presentation will only take about 20 minutes, and I think the demonstration will take about 20 minutes as well. And to finish off, 5 to 10 minutes of Q&A sessions will be done at the end. So first of all, basically dynamic analysis can be performed whenever you find this is relevant or not for your project. Also, you can also perform dynamic analysis when your clients, normally your clients or any other authorities or organization in charge, they normally request for this type of analysis. Apart from that, you can also refer to the underlying statement from the Eurocode. So basically, Eurocode provides us some sort of steps for us to decide whether the dynamic analysis is required for your project or not. So engineers can decide whether the dynamic analysis is relevant on this, based on this algorithms. So first of all, complexity of your structure or maximum line speed value. So if maximum line speed value are higher than 200 kilometers per hour, or if the structure is complicated or it is simple. So these kind of stuff can be used to determine whether the dynamic analysis is required or not. And also, we are interested in the vibration properties of the structure by comparing the natural torsional frequency. So comparing between natural torsional frequency of the structure and then the natural bending frequency of the structure. These kind of relationship can be also used to determine the whether dynamic analysis is required or not. And lastly, also maximum nominal speed can also be used to determine whether the dynamic analysis should be considered or not. Just to let you guys know, if you have any questions, you can write it on the question section in the webinar platform, and then I will try to answer the questions at the end of the demonstration. So if you have any questions, please feel free to write it on the question section. Okay, moving on. So in order to perform dynamic analysis, it is mandatory. So it is required to perform eigenvalue analysis before. So therefore, there are a number of eigenvalue analysis types available in Midas Civil. The first one is subspace iteration. So it is most commonly used, I guess, and very effective for large structures. And the second one is Lanczos. So it is very effective and efficient for the lower mode. And the last one is rich vector, and it calculates the vibration properties from the load case, from the whatever the load case that we defined, and it produces a reliable result with fewer modes. So in today's webinar, I will use this one, subspace iteration. So in order to perform eigenvalue analysis, you gotta have a mass data. So you need to have some sort of a structural mass information in order to perform eigenvalue analysis. So you can define the mass data using various methods in Madasibu again. So the first one is lumped mass. So distribution of the mass is concentrated at the node level. So we will have some sort of a diagonal matrix of the masses with the mass lumped at the node level. And then if you are using consistent mass, the mass matrix here is quite similar to stiffness matrix. So the masses are distributed all the way along the element, not just lumped at the node level. So the masses are distributed along the element if you're using consistent mass. And also there are various ways to apply masses from the load information applied to the structure. So stuff like self-weight are already existing on the structure. So you can use this function, convert self-weight into masses. So if you use this function, you can directly specify the direction, like convert to x, y, z, x, y, and z. So it will use the weight density information from the material properties that you defined, and it will automatically calculate the self-weight into masses. Along with self-weight, other load cases can also be defined and also be converted, such as nodal load or beam load, flow load, or pressure. So all of these load cases, so whatever the load cases that you have, you can select it here, and then you can put down the scale factor and then the directions as well. So if you use this, you can sort of convert whatever the load cases that you have into the mass data. And also for other load type, you can directly add the mass data using nodal masses function. So once you have finished setting up the eigenvalue analysis and the mass data, you can now define the time history load cases. So this is example of time history load case dialog in Madasibu. You can also define linear and non-linear time history load case. The good thing about time history load case in Madasibu is you can define several time history load cases within one model, considering different train speed and different type of time history analysis. So in order to compare the dynamic analysis result for different train speed, you don't have to have several different model file to obtain these results. You can have several different time history load cases which has different train speed for each of them. So you can obtain various results of different time history load cases within one model. We can perform linear and nonlinear time history analysis. So for linear type of linear analysis type, you can choose either model or direct integration for the analysis method, and you can choose transient and periodic for time history type. And if you want to perform nonlinear time history analysis, you can choose model, direct integration, and static. So you can choose all of these analysis type, but you can only choose transient for the time history type. for the nonlinear time history load cases. So now it is important to know what type of excitation is applied to the structure. So you need to know what type of loading we have to apply to the structure. So if we are considering earthquake or train load or pedestrian walking or jogging, we need to choose transient time history type. However, if you, for example, if you're considering a machinery, like with those which has some sort of a cyclic loading and pedestrian crowd loads, so these should be applied using periodic time history type. So today we'll be applying transient time history type train load using linear with the modal analysis type method. Moving on, one of the most complicated items to consider this type of analysis is damping. So there are 4 types of damping options are available in Midas Civil. The first one is the modal. It is most commonly used and also the most basic one. It is also specified in Eurocode for critical damping as well. And the method that we'll be using today is mass and stiffness proportional. So damping can be applied proportional to mass or stiffness information that you put. So if damping matrix is created by using this method, damping matrix becomes a diagonal matrix. So the biggest advantage of this method is that it uses smaller memory. So the amount of the calculation decreases quite significantly. So a huge amount of time can be saved. So I will be using this method today, mass and stiffness proportional. And strain energy proportional and element mass and stiffness proportional, also known as Rayleigh damping. So these damping methods are applied for more complicated structures, so structures with various material properties, so where each of them have different damping properties. So it is required to define the group damping for each material to apply for these type of damping method. So or when we use dampers or isolator in the structure, we'll be using this method as well. Before moving on, for the time increment, it is recommended to use 1/10 of the period of the highest mode for the initial value. So it is recommended to use 1/10 of the period of the highest mode for the initial value of the time increment. However, the natural frequency of the train can be quite influential, so it is required to try smaller time increment and see if the result converges or not. And for frequency for the mode 1 and mode 2, so mode 1 will be using the lowest mode, the frequency of the lowest mode, and mode 2 will be using the frequency of the highest mode after eigenvalue analysis. Also, Eurocode helps us to choose what dampings to be applied to the structure. So damping in this table is dependent on bridge type and the span length. Today, our example is using the steel. It is steel bridge, and the span length is more than 20 meters. So the lower limit of a percentage of critical damping is 0.5%. So this will be 0.005 in fact. Also, for the span less than 20 meters, we need to apply additional damping in order to avoid the resonance effect. So we need to use this equation. So if the span length is less than 20 meters, we need to use this equation to get this additional damping, and then use this the total damping for the structural damping on your structure, on your project. So once we have set up the time history load cases, we have to continue adding the load using function called train load generator. So this is the function called train load generator. So with this function, you can create any type of train loading. So if you have specific type of train loading, it can be generated relatively easily from this function. So the example today we have is high-speed loader model A. So and we can define the axle number and the length, the spacing between the axles, and the corresponding force values. So all of these values you can just simply input into this function and then create a train load. And also, if you have this data in terms of Excel, you can just simply import this onto this function and then use it. You just have to define the train velocity and the element size, and then this function will generate the train load automatically. And then what you have to do is this can be exported to time history forcing function. So this is a dialog of time history forcing function. And then we can continue with applying the load using dynamic loader load. So once we have time history load cases and the train load are generated using the train load generator to the time history forcing function, we need to apply these time history load cases into the structure using dynamic loader load function. So this is the example of dynamic loader load function. You just have to choose the time history load cases you defined earlier, and then you need to choose what sort of forcing functions that you will be using. And then of course you will be applying the structure in vertical direction, so direction global z and -1. So what you have to do is you will have to sort of apply this dynamic loader load all the way along the deck. So thinking of doing these steps individually by all the nodes separately, it is quite tedious and time consuming. So what I will introduce today is I will introduce how to use MCT command shell efficiently. So MCT command shell is, you can just think this as you can input data in the text format. So all the functions and all the information in my server can be inputted using this MCT command shell in this sort of a text format. And then you can just simply utilize Excel to generate these sort of series of data, and then you can just copy it and then paste it into this, and then you'll be it will be very easy to generate these sort of data at once. I will show you how to do this in demonstration step by step. So once we have performed the analysis, result checking should be done. So first we need to check the vibration properties of the structure. So these vibration properties, the model shape can be reviewed in both graphical way and table format. So we need to make sure that the mass participation is over 90%, so that we have adequate number of modes to check the structure. The model participation will be checked in global z direction in today's example. And then next, we need to continue checking the result of dynamic analysis. So deck acceleration is very important for preventing deck track instabilities, so such as like ballast instability, and also it is very important to improve the passenger's comfort. It can be checked for each node along the deck, creating nodal time history of acceleration against the time. So this is an example of acceleration, so deck acceleration against the time. And then, as I mentioned, you can have more than one time history function. So these have different train speed. So you can check these results together if you want to. And deck acceleration against the time, and you can also review the peak deck acceleration against the frequency. So these can be checked. Also, we would like to make sure that the excitation from the load does not match with the natural frequency. So if it matches with the natural frequency of the structure, there will be resonance effect. So we would like to avoid this sort of issue. The result can also be outputted in graphical format as well as the table format, as I mentioned, and it can be also exported onto Excel as well. So if you export this sort of data into Excel, you get all these numerical values of this dynamic analysis result. So you can also use Excel to use for your own spreadsheet as well. Also, forces and deformation need to be checked. So Eurocode states that we need to check the result of dynamic analysis with the result of the static analysis enhanced by the dynamic factor. So basically, we'll be creating this train load using dynamic northern load, and also we'll be creating the same thing using the static moving load analysis function in the civil. So we need to make comparison of the result between the dynamic and static analysis of the train load. So user can directly define a high-speed load model vehicle from a vehicle for static moving load analysis in the civil. And also if you choose LM1, so LM1 of SW0 or SW2 can also be defined where the dynamic factor can automatically calculated simply defining the determined length and the quality of track maintenance. Just like moving load analysis, time history envelope analysis result is available, which can be directly used in the load combination as well. So towards the end of our demonstration, I will simply compare the displacement result of the time history analysis result and the moving load analysis result as well. So for today's demonstration, we have excluded some sort of a basic modeling part. So basic modeling part is not included in today's webinar, and I will try to focus on how to perform eigenvalue analysis, moving load analysis, as well as dynamic analysis, and then finish off with just quick checking various results. Okay. So as I mentioned, the basic structure has been already prepared by me. So the modeling part is not included in today's webinar. So this is still bridge, and then I will start from how to apply eigenvalue analysis as well. So I have already defined all the materials and section properties and the boundary conditions to this structure. So let me just quickly add on the load information. So let's add self-weight onto the structure using this self-weight function. So click self-weight and -1 direction and click add. And also I will apply the secondary dead load. So superimpose dead load onto the structure precisely on the deck. So let me just quickly add this beam load onto the deck. So superimposed dead load or secondary dead load is applied onto the deck like this. Okay, so let's deactivate this on display. So as I mentioned, we'll be using subspace iteration method. So we need to go to analysis and eigenvalue. And we'll be using subspace iteration method. Number of frequency, let's just I have begun with a large number 80 and subspace dimension 180. Press OK. And as I mentioned, in order to perform the eigenvalue analysis, you need to have the mass data. So in order to provide mass data onto the structure, we need to go to the structure tab, structure type, and then if you click this option, convert self-rate into masses, you can then convert self-rate into masses in the global z direction. So click OK. And also, if you would like to convert the secondary dead load, superimposed dead load into masses, you can use load to masses function. So go to load tab, and then there's a static load. Then click load to masses function, and okay, we quickly. Let me close on my presentation first. Okay, so if we click load to masses, we can then choose the load case. So secondary dead load, we can choose this, and then we can select the direction, then the scale factor, and if we click add, we can then convert this load information into masses. So click OK. So now we have the mass data, and then we have converted this mass data load information into the mass data, and then we now have our eigenvalue. We now have set it up the eigenvalue analysis. Now we will generate the train load using train load generator. So go to tools and data generator. There's a function called train load generator. So click this. And if you click generate, you can then generate the train load using this dialog. So if you go to user define, you can define your train load information here. And if I have some sort of train load, the load model data in terms of Excel file, so this is the information that I have, so number of axles and the spacing between the axles, and then corresponding force value. So you can use this Excel information, and then you can just simply import it onto this function. Okay. And so you can just simply import it onto this function using this. You just have to define the train velocity. Let's write it as 300 kilometers per hour. And element size, let's put it down as 5. And then if you click OK, you can see that train load has been generated automatically. So you can save this in terms of TGS file, so that you can use this later on in time forcing functions as well. So let's close this. So once you have created the train load, now let's create train time history load cases. So first go to load tab and click dynamic load, and then go to time history function. So let's create time forcing function based on the train load that we just generated. So click import, and then we can then see the train load generated just now. So you can just simply open this, and then you can see that this has been imported onto this time history forcing function. And let's click OK and close. Now let's go to load cases to generate the time history load case. So click add. And let's name it as time history load cases 300 kilometers per hour. And then we'll be using linear model and transition time history type. And let's define this end time as maybe 10 seconds. And as I mentioned, the time increment, the initial time increment, the value is recommended to use 1/10 of the period of the highest mode after the eigenvalue analysis. So I have performed the eigenvalue analysis for this structure previous to this webinar, and then the period of highest mode was 0.02, so we'll be using 0.002, and I think this is small enough to give us a precise result. And for damping method, we'll be using mass and stiffness proportional. So we'll choose this and calculate from modal damping. You can also have mode 1 and mode 2. The frequency of mode 1 and mode 2 will be the frequency of the lowest mode after the eigenvalue analysis, and mode 2 frequency will be the frequency of the highest mode after the eigenvalue analysis. So this was around 1.894, and then this was around 50. So let's choose this. And then for the damping method, damping ratio 0.005 will be applied, and then 0.005 will be applied here as well. And coefficient of the damping is automatically calculated here. And then click OK. So now we have created time history load cases, and then close. So now we need to apply this train load using dynamic nodal load function. So click this dynamic nodal load. Now, as you can see that we can select the time history load cases that we just defined just right now, and also we can choose the forcing function of the train load, and of course we'll be applying this in global z direction, vertical direction, -1, and then the arrival time will be 0 for the beginning of the deck. So basically we will be applying the dynamic nodal load all the way along in the middle of this deck, and then click apply. And you can see that this dynamic nodal load has been applied at the middle, at the starting point. But think about doing this all the way along to the end, one by one individually. This can be quite time consuming and tedious. So let's just only activate this, and then see what the node number this is. The node number for this node is 397, and then it goes all the way along to 443. Okay, let's turn this off. So as I mentioned, we'll be using MCT command shell. So go to Tools and MCT command shell, and then you can see that all the information or all the function in Mother Civil is available in this sort of a command. So for dynamic nodal load, it is dyn and dynamic nodal load, and insert. If we press insert data, so you can see that this information, which is applied to the node 397, is this line. So basically, what I will be doing with this is I will just simply copy this, and then I will use Excel to sort of generate a series of data, series of information. Okay. So basically, I already have this, but let's just delete this. Okay. 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 So this is the information that I have. So let's just making it quite as neat as possible. So second column, and the third column, and the final one, and delete this information. So basically, what this actually means is that you can see that this data information has been inputted in this line. So the first one is the node information, and the second one is time history load cases, and the third one is the forcing function, and the next one is the direction, and the next one is arrival time, and the last one is the scale factor. So we have created train load with 300 kilometers per hour velocity. This is about 83.3 meters per second. So spacing between two neighboring nodes was 5 meter in our case. So this is 5. So time taken for the train to move 5 meter was about 0.06 second. And then we'll be using this plus this again. And then we'll just generate this. So basically, what this represents is at node 397, the arrival time will be 0, and the node 398 will be the arrival time will be 0.06, and the next one will be 0.12, and this will go all the way along to 443, where the deck finishes. Okay. So let's just generate this all the way to 443, and let's do this. So now we have all the dynamic nodal load information to node 397 to 443. So let's just copy this, and then let's delete this, and then just copy and paste. And make sure to delete this information, otherwise you'll be duplicating the information, duplicating the dynamic nodal load information. So let's just click Run. So now you can see that the dynamic nodal load has been generated automatically using dynamic nodal load function. So this is quite a convenient tool sometimes if you find it difficult to only utilize the function in the model window. You can just simply use this MCT command shell. So all the information can be handled in terms of text format. So you can just, so if you click Insert Data, you have all the information in terms of text format. So node number 1, 2, 3, all the way to the end, and the coordinate. So you can access and then you can modify all the information in terms of text format. So this is quite useful sometimes. So now we have finished creating the time history load cases for this structure. Now what I want to do is I want to create a static train load. So using my moving load analysis in MyDecibel. So go to Load, Moving Load, and click Eurocode. And the first step is you need to define the moving load code, and then you need to create a traffic line name. So let's create lane 1, and I want to create the traffic lane at the middle of this deck. However, as you can see, there is no longitudinal beam element in the middle. So what I will be doing is I will be using the beam element at the end, and then I will use this as a reference element, and then I will just apply some sort of eccentricity, the distance between this reference element to the middle. So I will use this eccentricity to create the traffic lane at the middle. So in order to do that, go to Query and Node, and if you click the first one and then second one, we can see the distance between these two nodes is 4.067. Okay, so I'll be applying -0.067 eccentricity. Now I'll be using cross beam type for the vehicle load distribution, and then I have defined the cross beam structure group previously. So cross beam has been selected, and then I will start from this element all the way to the end, and then simply click OK. And then you will be able to see that the traffic lane has been generated at the middle of the stack information using this reference element. So let's then move on to vehicle load and vehicle, and click Add Standard, and you'll be able to select road bridge or footway or footbridge, road bridge or fatigue. And I'll be choosing rail traffic load, and then I will choose high speed load model A. And you can choose once you finish doing comparison between the static train load and the dynamic train load, you can then obtain dynamic factor, and then you can apply the factor later on. But now I will just simply just leave this and then create this vehicle. Click OK. And what we'll be doing is we'll be creating the moving load cases. Click Add. And let's name this as moving load 1. And then click Railway Bridge. And then click Add. And then you will be able to select the vehicle that you have created, and also you will be able to assign this vehicle on the lane that you just created now. So click OK, then close this. So the input has been finished with this. Dynamic node load has been successfully inputted, as well as the static train load. Before performing the analysis, we need to make one modification. So go to Analysis and click Moving Load Analysis Control. And I want to provide you some tips and for the calculation speed. Before that, we need to change the load point selection into all points. This is because the moving load analysis in Model Civil is based on influence line analysis. So the train will be positioned at the most critical position based on the influence line analysis. So influence line result. However, if you think about a train, you cannot sort of split the train in the middle. So you cannot position train at this part and then deactivate at this part and then activate again at this part. So you cannot do this for the train. So we need to choose all point. So we need to make sure the train moves all the way from the beginning to the end consecutively, rather than being activated at only specific position based on this. This is more useful for the normal traffic vehicle. So you have to bear in mind we need to choose all point in moving load analysis control. And in terms of calculation filters, we can sort of decrease the amount of calculation, and then we can significantly reduce the time of the analysis using this by applying these filters. So basically, what I've done is I have created a deck as a structure group. So I made this as a structure group because we are only interested in the analysis result at this deck. I have made this as a separate structure group, and then what this will be doing is the moving load analysis will be calculated based on the group that you specified rather than the whole structure. So this will save quite a lot of time for the analysis, and you can also utilize this feature a lot of times. Not only these projects. So if you have some sort of a really complicated or large project, you can use various filters to sort of shorten the amount of analysis rather than analyze the whole structure. So this is some sort of tips for you. And click OK. So all the input has been finished for this model. So I have prepared a completed model file, exactly the same. So just to save some time to analyze the structure, I have prepared this completed model file. So I'll show you how to check some of the result and then finish off. So for first of all, as I mentioned, we need to go to the vibration mode shape, and then we need to sort of check the model analysis result. So you can choose different model, and then you can activate legend, and then you can check various mode of the structure. So first of all, you need to make sure that the mass participation is over 90% of the project. So as you can see, the mass participation is over 90%. So the number of frequencies is actually adequate. So this is fine. The analysis is valid for this eigenvalue analysis. Okay, so let's. I want to show you how to check the time history analysis result. So if you go to result, time history graph. Before that, let's go to time history result and then displacement, velocity, and acceleration. So if you go to this, you'll be able to see displacement result, velocity result, acceleration result for this time history load cases that you have at different time steps. So these are the time steps that we have taken into account. So for different time steps, we can obtain various results. So these are all provided, and also you can create some sort of animation of this dynamic analysis result as well. So let's go to time history graph. So in order to plot time history graph, we need to make some sort of function. So let's click define and modify function. And what I will be doing is I'll be creating a new function for displacement, velocity, and acceleration. And we need to select node information. So if you want to review the displacement, acceleration, displacement, velocity, and acceleration result at this specific node, you can just simply click this. So the node number is 418. So let's just write it as deck acceleration at node 418, and then reference point at ground motion, and then the component will be, of course, global z direction, and time history load case is this one, and then create this time history result function, and then close. And then let's go back to the time history graph again, and then you'll be able to see the function that the result function that you just created. So I'll click this and then add it onto this list, and then you can name this graph deck acceleration, and then number of decimal points, let's just make it as 1, make it as 1. So if you click graph, the program will automatically generate the time history graph. So the x direction will be the time, and the y direction will be the acceleration. So these are the time history example of time history graph that you can obtain from the analysis. So you can zoom in and you can zoom out, and you can do various kind of stuff with this. And if you right click, you can change the x-axis from time to frequency. So if you want to review this the acceleration result against the frequency, you can review this as well, and then you can check whether this is affecting the resonance effect by matching with the natural frequency of the structure or not. So you can check these results as well. And then you can plot more than one function. So you can plot more than one train speed against on the same graph. So you can use this information. You can use this function. And apart from that, another stuff. The last thing that I want to show you today is the comparison between the displacement from time history result and the static moving load analysis result. So if you go to deformation, displacement contour, and then you can see that the time history load cases, you can access this from here, and the moving load analysis result as well. And if you click time history max, and then let's just review this in DZ, and then we can just click where the acceleration is the maximum. And also we can turn on the legend as well. And we can also compare this with the moving load maximum result as well. So 3680, and then this was 4.26, I think. Let's compare the displacement result for the time history load case in DZ direction. The maximum displacement was 5.4 millimeter for time history load cases, and then the maximum displacement for static moving load analysis result was 4.26 millimeters. So yeah, so you can sort of compare these results and then obtain dynamic factors to sort of apply onto the moving load analysis result later on to check various member forces and displacement and bending moment, that sort of stuff as well. So this is what I have prepared for the demonstration session. Just to quickly introduce, and before finishing off today's webinar, I want to introduce another feature called rail structure interaction. So this is not the rail to track interaction, so the vibration will not be considered in this wizard. But using this rail structure interaction wizard, it is very handy and convenient to create this sort of structure with the rail information connected to the structure. So we will be able to create this structure automatically. This is like a wizard. So we have this railway, and then this will be connected to the top of the PSC girder bridge using a multilinear elastic link, and then this the PSC girder bridges will be automatically generated as well using the section properties that you already defined. So I would like to have another webinar based on this RSI of Mitre Civil later on. So please keep updated. And then this function, we will be able to plot this axial stress result due to temperature variation in the deck, braking and traction, and vertical load of the train load. So all of these results are automatically available in the report function. So we will try to have another webinar based on the RSI function of Mitre Civil later on. So thank you for joining our webinar today. So if you have any questions, please ask us anytime in the email below, and I can answer some of the simple questions now. So one of the questions from Daniel about the load to message function. So basically the reason why I have applied the scale factor as 1 is because that the secondary dead load is already applied in the global z direction in minus global z direction, so I don't have to specify the scale factor as -1 here, so I just left it as 1. So for instance, if the load will be going outward, obviously you will have to consider this in -1 direction, but this is not relevant in this case. And another question related to how to check the dynamic displacement result and static moving load analysis cases result. So if you go to deformation, then again, this is the last thing that I have explained. So you choose time history max, and then let's go to value, then just only activate maximum only. So if you click OK, you can see that the maximum displacement is 5.4 millimeter at this position. So the maximum displacement is occurring at the node 311, which is here, and the maximum displacement for the moving load is occurring at 505, which is this one, and this is 4.265 millimeter. So what you will have to do is you will have to sort of compare the result. So let's say node 311 and 505, and then time history result and the moving load analysis result. And if you click OK, let's just change this. So okay, so for node 311, the displacement result is 5.44 for time history load case, and the displacement is 3.89 for moving load result. So what you will have to do is you will have to divide this value using this, and then you will be obtaining some value, something like 1.3 something, and then you'll be dividing this value with this simple static moving load result as well, and then you'll be obtaining another value about 1.08 or something. And then what you will be doing is you can just choose a larger value to approach more conservatively to obtain dynamic factor. So I think you will be better off choosing these two comparisons. So if the maximum displacement position is different, so this is what you can do to sort of how to choose the dynamic factors. So there's more number of questions that I have received from Bogdan, Thea, Konstantinos, Yuxin, and Dimitris, and I will answer these questions via email. So, and also if you have any more detailed questions, please let us know at any time through this email address. So uksupport@midasuser.com. We'll be able to sort of obtain the questions from the webinar. So we'll be happy to answer all of your questions via email as soon as possible. So thank you for joining our webinar today, and then we'll be also happy to get some feedbacks from you as well. Thank you.